For step 4b, we can compare the p-value or probability value with some alpha criterion level or significance level. The p-value, it's sometimes denoted just with p, is the probability of obtaining a test statistic as or more extreme than the one we actually obtained. So for a two-sided test where the alternative is that the population mean does not equal the claimed value of the population mean under the null hypothesis, the p-value or probability value is simply the probability of obtaining a test statistic as or more extreme than the one we obtained in absolute value times 2. We multiply by 2 because we want to take into account the fact that we're agnostic whether we have an extreme test statistic in the left or right side of the distribution. For a right-sided test, where the alternative is that the population mean is greater than the claimed value of the population mean under the null hypothesis, the p-value is simply the probability of obtaining a test statistic greater than or equal to the one we actually obtained. That's because we're only interested in examining whether or not the population mean is greater than that of the claimed value under the null hypothesis. For a left-sided test, where the alternative is that the population mean is less than the claimed value under the null hypothesis, the p-value or probability value is equal to the probability of obtaining a test statistic less than or equal to the test statistic we actually obtained. So in either of these instances, we reject the null if the p-value, probability value, is less than or equal to the alpha criterion level. That's just the probability of a type 1 error. It's the significance level. And if we have a p-value less than or equal to alpha, then we say our findings are statistically significant and we reject the null hypothesis at that particular level of alpha. So let's see how we can apply the p-value approach for making a decision about some kind of claimed value about the null hypothesis. So suppose we have these following three test statistics. These are z-test statistics. We're going to look at a z-test statistic of 0.85, one of 4.92, and one of negative 1.99. The idea behind this is with an alpha level of 0.05, what would we conclude if we computed p-values with a two-sided z-test, a right-sided z-test, and a left-sided z-test for each of these z-test statistics? So here we are going to examine p-values with a z-test statistic of 0.85. So we can see that our z-test statistic lies right here on this model of the sampling distribution. And we can chunk off the distribution in these two areas. We can find the probability of a z-test statistic less than or equal to 0.85 and also approximately greater than or equal to our z-test statistic. And we can conduct a two-sided test using p-values, all right? For a two-sided test in which the alternative is that the population mean does not equal the claimed value of the population mean under the null hypothesis, the p-value, again, is just the probability of obtaining a test statistic greater than or equal to an absolute value of the one we obtained. So we can see that that blue shaded area, all right, that is the probability of obtaining a z-test statistic greater than or equal to the one in absolute value we obtained, because we obtained 0.85. The absolute value of 0.85 is 0.5. And so that area on that blue shaded region of the distribution is about 0.198. So we multiply that by 2 for a two-sided test because we want to take into account the fact that we are agnostic whether we have an extreme test statistic in the right or left tail of the distribution. And we have this p-value of 0.396. Now this is the probability of obtaining a test statistic as or more extreme than the one we obtained under a two-sided test. And this is greater than alpha of 0.05. The p-value of 0.396 is greater than 0.05, so we fail to reject the null using a z-test statistic of 0.85 under a two-sided test. We could also conduct a right-sided test using this particular z-test statistic. For a right-sided test, where the alternative is that the population mean is greater than the claimed value under the null hypothesis, the p-value is simply the probability of obtaining a z-test statistic greater than or equal to the one we observed. That probability is simply 0.198. This is again greater than alpha of 0.05. So for a right-sided test, we would again fail to reject the null hypothesis. We can also conduct a left-sided test using a z-test statistic of 0.85. For a left-sided test, right, for all of these tests, the null is the same, but for a left-sided test, the alternative is now that the population mean is less than the claimed value of the population mean under the null hypothesis. So for this kind of test, a left-sided test, the p-value is the probability of obtaining a z-test statistic less than or equal to the one we obtained. So the one we obtained is 0.85, and the probability of obtaining a z-test statistic less than or equal to the one we obtained is that entire green region, which is equal to 0.802. The area under that curve for that green region is 0.802. And it's quite likely that we would obtain a z-test statistic less than or equal to the one we obtained. So when we compare this probability of value to 0.05, it's much larger. So again, we fail to reject the null hypothesis. So you can see with the z-test statistic of 0.85, under a two-sided, left-sided, and right-sided test, for each of those instances, we fail to reject the null. This reflects the fact that 0.85 is really not that extreme of a z-test statistic. Let's examine p-values with a z-test statistic of negative 1.99. The idea, again, is we can use the z-test statistic, its location on the standard normal distribution, to obtain probability values, and then we compare these probability values to our alpha criterion level. So our z-test statistic of negative 1.99, it lies on the left-hand side of the standard normal distribution, and you can see that we can chunk this distribution into two regions, right? Two sets of probabilities. The probability of obtaining a z-test statistic less than or equal to negative 1.99 is pretty small. It's 0.02, right? That's only 2% of the time would we expect to have a z-test statistic more negative than negative 1.99 given this particular null hypothesis. The probability of obtaining a z-test statistic greater than or equal to negative 1.99 is quite likely. Right? It's very likely that you're going to have positive, or somewhat negative z-test statistics. So let's use this information, this standard normal distribution and this z-test statistic, to make inferences and conclusions. So let's examine a two-sided, right-sided and left-sided test. So for a two-sided test, right, where the alternative is that the population mean is not equal to the claimed value of the null hypothesis, the p-value is simply the probability of obtaining a z-test statistic greater than or equal to the one we obtained in absolute value times 2. So the absolute value of negative 1.99 is 1.99. And so when we multiply the probability of obtaining a z greater than or equal to 1.99, which is 0.0233 times 2, we obtain a particular probability value that is a little bit less than 0.05. For a right-sided test, where the alternative is that the population mean is greater than the claimed value under the null hypothesis, the p-value is the probability of obtaining a z-test statistic greater than or equal to the one we obtained. That's very large, as we just saw. That's 0.977. It's very likely. So under a right-sided test, we would fail to reject the null hypothesis because 0.977 is much greater than our alpha level of 0.05, the benchmark by which we compare our p-values and make a decision. For a left-sided test, where the alternative is that the population mean is less than the claimed value under the null hypothesis, the p-value is simply 0.0233. That is, the p-value is just the probability of obtaining a z-test statistic less than or equal to the one we obtained of negative 1.99. So you can see that with alpha of 0.05, we can reject the null hypothesis for the two-sided and left-sided tests only. We do not reject the right-sided test because 0.977 is much larger than our benchmark of 0.05. Keep in mind, what we're doing here is we're comparing our probability values to this level of alpha. If our probability value is less than or equal to our level of alpha, then we reject the null at that particular level of alpha. All right. Let's examine p-values with a z-test statistic of 4.92. Right, this is an extreme test statistic, you can already tell, because 4.92 lies on the standard normal distribution. And again, we can locate the z-test statistic on the standard normal distribution. This is a model of the sampling distribution. And our z-test statistic is way out here on the edge. And you can see that it's very likely that we would obtain a z-test statistic less than this particular value if the null is true. If the null is true, it's very unlikely that we would obtain a more extreme test statistic. The probability of obtaining a z-test statistic greater than or equal to 4.92 is almost zero. You round down to zero. It's never exactly zero, but it gets very, very close to zero. So let's use this information, right, to make some decisions. So let's examine a two-sided test. For a two-sided test in which the alternative is that the population mean does not equal the claimed value under the null hypothesis, the p-value is simply 2 times 0, which is essentially 0. It's not exactly 0, but it's very close to 0. So in this case, comparing that p-value to 0.05, it's less than 0.05, so we would reject the null hypothesis for a two-sided test. Again, this is just reflecting the fact that a z-test statistic at 4.92, it's quite extreme. It's pretty large, so we'd expect a low p-value. We'd expect a low probability of obtaining a test statistic more extreme than 4.92 under the assumption that the null is true. For a right-sided test, where the alternative is that the population mean is greater than the claimed value under the null hypothesis, the p-value is basically 0. It's just very unlikely that we would obtain a more extreme, more positive test statistic than 4.92. For a left-sided test, where the alternative is that the population mean is less than the claimed value under the null hypothesis, the p-value is nearly 1. That just reflects the fact that the z-test statistic is so extreme, so positive, it's really quite likely to obtain, under the assumption that this null is true, any range of z-test statistics from 4.91, 4.5 to -5 to 2. It's very likely to have a wide range of z-test statistics less than 4.92. Right? So in conclusion, with an alpha level 0.05, we reject the null hypothesis for the two-sided and right-sided tests only. Right? So the idea is, with a p-value approach, in contrast to the critical values approach, we use our z-test statistic, we locate our z-test statistic on the standard normal distribution, we assume the null is true, and then the p-value, you can think of it as a measure of inconsistency. Right? If that probability value is low, if the p is low, the null must go. You must reject the null. And it suggests that, in fact, if the null is true, our data is pretty inconsistent with the null. So you can think of the probability value as a measure of inconsistency. The larger the p-value, the closer it is to 1, the more consistent our data is with the null hypothesis. The lower the p-value, the more inconsistent our data is with the null hypothesis, suggesting we should reject the null. And with that, we will do some explorations of how to work with p-values and understand them when making a decision in the framework of a hypothesis test.